So does that part also make sense?
Yes.
Okay, sounds good. Have you seen something like that before?
No.
No? Okay. So this is called an MRI. So sometimes what doctors do is they scan your body just so that they can see what's going on inside of you and what your internal organs look like. This is the brain. It's yeah, this is actually what the brain looks like if you were to give it a scan, an MRI scan. What an MRI scan is this? So you see this red circle right here? It's a proton. And you remember what charge the proton was? Positive or negative?
Poppy.
Yes, positive. That's correct. This entire circle right around here in this machine, that entire thing is made of magnets. And so this entire big device will release these curly looking lines that are called magnetic waves. One of these devices, when they send out these waves, they also send out these green waves. And these are called radio frequency waves. To the right or to the left was the arrow pointing.
To the right.
Yes, that's correct. Here it's pointing to the right. And that's because the other radio waves that the MRI device brings in causes the proton to rotate from left to right. When the green ones disappeared, the proton rotates itself back to where it started. And when that happens, the MRI captures that release of energy that the proton releases when it moves back to its original position. And that's why we get to see things like this. So there are different equations for Maxwell's equations. There's an integral form of it and a differential form. So basically Maxwell's equations talks about the relationship between magnetic flux, magnetic field strength, and what the area or the surface that it's actually encompassing. The magnetic flux basically is like a measure of how much of that field is going through a specific area. This is just like a very simple thing, just showing the relationship between Faraday's law and then Faraday's law of induction, specifically with one turn of the coil. So this is the derivation for the differential form of Faraday's law of induction. We went directly from E dot ds to the curl of E d. That actually applies Stokes' theorem to equate that relationship. We can directly simplify it to become just the curl of E plus the differential of the magnetic field strength. And this would be for a uniform magnetic field. That's why we can bring out the B in the integral form. We get the differential form of Faraday's law of induction.
I think that's like interesting. Like there's also a related magnetism thing called eddy current breaking. I don't remember exactly how it works. It has to do with let's say you have like a plate of metal traveling very quickly over other plates of metal. So think of like, maybe a 12-foot long like sheet of aluminum, and you have another sheet of aluminum attached to the train that goes right over the long strip of aluminum. So it's not touching, there's no friction, it just travels right above it. And when you run current through the top plate of metal, that current will generate like a counter force in the longer aluminum plate underneath.
So that's basically like induced magnetic field, right?
Yeah. So you use an induced magnetic field to like help break. Yeah, there's a lot of really cool things. There's a thing called a coil gun. Wait, do you know about it?
Solenoid?
Yeah. Well, essentially you take out the solenoid and you make a bunch and you like string a bunch of them together. You can like shoot a metal, if you put a metal marble through it. Yeah, you just it like shoots it out. It's really cool. Really cool.
Yeah, you would have to connect that to like the battery, right?
Yeah. But like if
Yeah.
you chain the solenoids, it like you pull it, and once the metal like ball bearing goes through the middle, then you turn it off. Or actually, you can like invert it to then like push it out.
Now, SQUIDs are based on superconductivity. Superconductivity is a phenomenon in metals that lose all their electrical resistance. And the basic point is that the electrons in the metal are paired together in what's called Cooper pairs, and they have a charge of 2 electrons. And all the current in superconductors, I've tried to show here, is carried by these Cooper pairs. And it's a low temperature phenomenon. If you have a closed loop of superconductor and it has some magnetic flux trapped in it, which of course generates a magnetic field,
yes,
then it's quantized in units as what's called the flux quantum. We're getting towards the origin of the name SQUID. These Cooper pairs that carry the current, if you put an insulating barrier in their way, they can go through it by what's called tunneling, which is a very, very important effect in quantum mechanics. And it's all explained by large numbers of equations using lots of calculus. He predicted this in 1962, and it was observed in 1963. And what they showed was that if you make one of these devices and you cool it down and you pass a current through it at very low currents, no voltage is developed, and then it makes a transition to a voltage regime. And we'll get to that. So finally, what is a SQUID? The SQUID consists of a superconducting loop, but these two X's mark Josephson junctions. If you make one of these loops and cool it down, again, you get this zero voltage regime, and then it becomes a resistor. But if you apply a magnetic field to the loop, you find that the voltage across the loop oscillates as you increase the magnetic field. The distance between these two peaks is this flux quantum that I just introduced.
I see.
And that is why it's called the superconducting quantum interference defect. Today's devices are made out of thin films of superconductor, and they're deposited on silicon wafers or whatever in incredibly small sizes these days. All the SQUIDs that are used today in all these different applications measure the equivalent of something like that.
Do you think you could, talk to us about some of the research you've done?
Yes, okay.
Yeah.
Searching for dark energy. The idea is that if you could really figure out the density and the position of these clusters, and it would take thousands of them, you could imagine working out a theory for dark energy. There are now many telescopes around the world looking for these. In the early 2000s, one of my colleagues, he came to see me and he said, you know, we really need to improve the speed with which we can read out our telescopes for exactly this kind of application. And he said, do you think you could give that some thought? And I said, well, you know, give me a week or two or three. And I did. I figured out how to increase the speed of the readout by a very large factor. And here's a photograph of this particular telescope. It has 24,000 SQUIDs doing the readout with this technique that I work. Here is now an early version of an ultra-low field MRI system imaging the brain. And it's working at 100, 150 microtesla. So as promised, it's about 4 orders of magnitude smaller. In fact, the principal advantage is that it has much better contrast between different tissues. And for example, it's quite difficult with conventional MRI to image cancer. With this ultra-low field, you get a very, very good contrast, and we've published papers on that.
Is the reason why it has much better contrast between the different tissues because our cells have magnetic fields, so the smaller, they can detect the magnetic fields, the clearer that is?
That's a very good suggestion. It turns out that it's a somewhat different reason. Because the field is lower, the frequency of the MRI is much lower. And the frequency of the MRI, and this is part of the reason why we got into this, is much closer to the frequency of cells. So cells have these inherent relaxation times, which gives them a characteristic frequency. And then one of my favorite applications is magnetoencephalography. This is a system to measure magnetic signals from the human brain. It enables one with incredible sensitivity to see what's going on in the brain. In that kind of system, there are no fewer than 306 SQUID channels, and it has to be in a very magnetically shielded room because it's looking for these tiny signals. Your brain, as you sit there listening to me, your brain is putting out unbelievable amount of magnetic stuff. I could flash lights in your eyes, and that would enable your brain to respond, and I could see if your brain is working properly. And again, there are many, many applications of this. One of the things that they can do is to look at the signals coming from sources around the brain tumor, and you can go into the brain in a way that won't damage anything else.